Hello, students. Since our first attempt failed and our second attempt succeeded, let's try to think about what went right here. Well, what I did is I took an x and a 1, which would normally be a basis for P1, and I just paired them with 0. And here I took what would normally be a basis for R, and I paired that with 0. So maybe in order to get a basis, well, maybe we could conjecture something like this. If B1, B2, LM, let's do M, is a basis for V, and C1, C2 through Cn is a basis for W, then the set of all Bi 0, so that I is in 1 through M, together with the set of all 0 Ci, so that I is in 1 through N, is a basis for V crossed with W. Okay, so let's try to show this. Proof. Well, what do we show? We want to show it spans and that it is independent, right? So let's see if it spans. Well, for any little VW in big V cross big W, we can write V, little v, equals, I'll use alpha 1, beta 1, through alpha m, beta m. And we could write W as, well, now I don't want to use, I have alphas and B's. I'll use deltas to go with the C's. This way we don't have any direct, it feels right. Okay, so I have delta 1 C1 through delta n Cn there. And then what could I do? Well, I could take alpha 1 B1 0 plus all the way through alpha m Bm 0 plus delta 1 0 C1 all the way through delta n 0 Cn. And what does this equal? Well, this equals, when I put this all together, I get alpha 1 B1 plus alpha m Bm, and then I get delta 1 C1 plus dot 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 delta n Cn, which is just little v, little w. Oh, and I should have put that in parentheses. I left out the parentheses there. It's not just a stray v in V cross W, it's a pair VW inside V crossed with W. Okay, so what does this show? It shows that we have span, that these elements span the space V cross W, but it doesn't show independence. So suppose I need now to show that these are linearly independent. Well, I'll say if alpha 1 B1 0 plus alpha m Bm 0. And I'll name these constants alpha 1, alpha m, delta 1 through delta n, so they match. It'll mean we have less work to do because we know what this is. So if this equals 0, and here this 0 means the 0, 0 inside our field, what do I know? Well, I know that alpha 1 B1 through alpha m Bm and delta 1 C1 plus delta n Cn is equal to 0, which once again, this is, by 0 I mean the 0 comma 0 inside V cross W, that we could write 0 in any case. Well, what does that mean? The only way that this is going to give me that 0, 0 is if I have alpha 1 B1 plus alpha m Bm is 0 and delta 1 C1 plus delta n Cn is 0. And since these are both bases, I know that alpha I and delta I are all 0. So that shows independence. So this shows that this is a basis. And what would the size of this basis be? Well, how many elements do I have here? I have m. How many elements do I have here? I have n. I'm going to get, since this is a union, m elements here, n elements here. There's nothing in common, so there's no canceling out or anything else. So I have dimension m plus n. So we also just proved that the dimension, I should say if v and w are finite dimensional, then the dimension of v cross w is the dimension of v plus the dimension of w. And notice that this works a little differently than in other places. So even if we haven't had too many different math courses in like groups and topologies and things like that, just when it comes to the Cartesian product of sets, right, if I take the absolute value of the set v cross w, and let's say these are finite. So let's say v is finite and w is finite. Well, then this is the size of the set times v times the set w. And if I have groups, if I have the size of the group G1 cross G2, well, this is actually ends up being the size of G1 times the size of G2. I'll put a little dot there to make that pretty. So in many places, when we take the product, we get a multiplication. Here, even though the product is kind of behaving like multiplication, remember, dimension is not the same thing as number of elements. Dimension is a statement about how many elements we have in a basis. And in this case, we get plus. And of course, this would generalize to more spaces too. So if vi is finite dimensional, and this is for all I in some finite set, I would have the dimension of v1, v2, through Vn would be the sum of each of the individual dimensions, which I could also write as dimension of V1 plus the dimension of V2 plus the dimension of Vn. So this works in general. So what do we know so far? We've looked at least one example. Exactly one example, to be more accurate. We've found a basis for a product vector space, and we found a statement about dimension. Now that we know what the basis is, we can make a statement about dimension, which we did. So those are some results on finite dimensional vector spaces and the dimension of their products.